Hi, I'm David Bonsack, Product Manager for Rheology at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by arranging the windows to your liking. You can resize the video and slide windows independently from one another by clicking and dragging at the bottom right-hand corner of each window. If you get disconnected at any time, please use the instructions you've received to log back in. You can access several different content windows by clicking at the widgets at the bottom of the screen. These include speaker bios, additional file downloads, and social media interactions. And if you need help, click the question mark widget. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. Our guest speaker today is Dr. Bharath Rajaram of TA Instruments. Dr. Rajaram is a product specialist in the Rheology group at TA Instruments, where he is involved in new product development and commercialization. Bharath received his master's and PhD in chemical engineering from the University of California, Irvine, where he worked with Professor Ali Meraz. His doctoral thesis focused on using confocal microscopy to understand the relationship between rheology and microstructure of colloidal gels, with an emphasis on the nonlinear rheology of these materials. It's truly a pleasure to have Dr. Rajaram speaking with us today. The title of his talk is Rheo-Microscopy, Bridging Rheology, Microstructure, and Dynamics. Bharath?
Thank you, Dave. Hello and welcome to today's webinar, where I'll talk about using optical techniques, specifically microscopy, to explore relationships between rheology and a sample's microstructure and its dynamics. Today's talk is outlined as follows. I'll start off by introducing published examples from published literature where microscopy has been used to gain insights into sample deformation, rheology, and its microstructure. I'll talk about the new modular microscope accessory that's available for the DHR rheometers. And I'll talk about specific examples using both qualitative and quantitative microscopy across a wide spectrum of samples to highlight how microscopy can be used to understand structure. So there are a number of methods available to probe and investigate the relationship between a sample structure and its bulk rheology. Of these, scattering and microscopy are probably the two most popular methods. There are other methods available like MRI velocimetry and UV speckle velocimetry as well. Scattering techniques basically involves shining a light or neutrons or X-rays on the sample. It interacts with the sample and forms a pattern. Depending on how the orientation of the sample and the dynamics of the sample, the nature of these patterns change. Scattering is a fairly sensitive technique in that it can pick up structural and dynamic changes, but it is inherently an ensemble average technique, meaning the pattern that you're seeing is a collective sum of the light or X-ray interacting with the entire sample. And as such, it's not possible to pick up on local or rare events that might be taking place in the material. Analysis of scattering techniques are not necessarily straightforward, and access to X-rays and neutron beam lines is somewhat limited. Microscopy, on the other hand, is just direct visualization. We're viewing the sample, and it can be done in a number of different modes, including Brightfield, Fluorescence, Cross-polarization, confocal, DIC, and so on. Because we're directly viewing the sample locally, we can observe local events, rare events such as breakup or coalescence, that would not be picked up in scattering techniques. And interpretation is relatively straightforward because what you see is what is going on in the sample. There have been many attempts to try to look at the sample and try to connect the rheology with the quiescent structure. And I'll walk through a few different examples in published literature. The first example we're going to look at is oil and water emulsion that's been stabilized with a glycolipid stabilizer. And we're looking at the effect of the stabilizer chain length on the sample rheology. Shown on the left is a plot of the shear viscosity of the sample as a function of shear rate. And we notice that as the stabilizer length increases, so looking at the C10 stabilizer, for example, the sample has a pronounced shear thinning behavior and has somewhat of a little bit of a yield stress as well. as the length of the stabilizer decreases, we transition more towards a Newtonian type behavior in this specific example. We can also look at the critical strain, where we look at the strain at which we see a departure from linear viscoelasticity and plot that for these different stabilizer materials. And again, with the C10 or tessile material is the most stable of the lot. It has the greatest critical strain as measured through linear viscoelastic strain sweeps. If we look at the microstructure of these 4 different emulsions, we can see they're fairly different. For C7 and C8, we see a broad distribution of droplet emulsion sizes. And C9 and C10, as we increase the length of the stabilizer, the droplet size becomes much, much smaller. So we can rationalize this behavior that we're seeing in terms of bulk rheology, the shear thinning behavior, and the critical strain dependence, in terms of the stability that these long chain stabilizers bring to the emulsion that's being formed. Increasing the strain length, chain length of the stabilizer leads to smaller droplet sizes, brings about some sort of a yield stress, and also improves the stability of the emulsion that's being formed. Here's another example where we're looking at rheology and trying to connect that with quiescent behavior. In this case, we're looking at 2 different types of collagen gels. The first set of pictures show native collagen gels, where we have collagen just by itself, and then composite collagen gels, where we've also added hyaluronic acid to the sample. As the sample gels, we're looking at the data on the left show time sweeps, where we look at the evolution of G prime and G double prime of these materials. We see a crossover and then a development of a storage modulus plateau. And of course, the magnitude of the plateau depends on the concentration of collagen that's being used. Greater the concentration of collagen, greater the storage modulus of the materials. Addition of hyaluronic acid doesn't necessarily seem to affect the magnitude of the gel, the strength of the gel that's being formed, at least not on a log scale. But if you look at the time that it takes for these gels to form and arrest, it certainly has an effect. So the micrographs on the top and the bottom show the gel structure at the time of arrest. When we're viewing these micrographs, the time of arrest in this paper was defined as time at which the individual collagen fibers stop moving. So we can see as we bump up the collagen concentration, the time to arrest goes from about 9 minutes to 6 minutes. And at each corresponding collagen concentration, introducing hyaluronic acid decreases the time for the time to arrest. We'll also notice that at the time of arrest, there are more fibers, a greater number of fibers that are visible when we have hyaluronic acid. And the operating theory here is the increased viscosity due to the addition of HA retards the movement of these fibers, and they arrest, or the collagen fibers, they just get arrested in place. Here's the third example that we look at in terms of connecting rheology with quiescent structure. In this case, we're looking at a colloid polymer mixture of charged silica particles mixed in with a polymer of opposite charge. So the colloid and polymer of opposite charges, so obviously when you mix them together, the polymer wants to stick onto the colloid. And depending on the polymer concentration and the colloid concentration, the free polymer can effectively bridge or form a bond between 2 or more colloidal particles. As you start to bump up the polymer concentration, enough colloidal particles get bonded or arrested, and you can form a sample spanning network or a gel. So in these materials, we see classic rheological signatures of gel-like behavior, such as a storage modulus plateau at low strains and the presence of a yield stress. The plot on the left shows the evolution of the storage modulus plateau and the yield stress as a function of the polymer concentration. And we notice a fairly interesting rheological behavior. So as we start to increase the polymer concentration initially, the strength of the gel that's being formed increases, goes through a maximum, and then beyond a certain point, adding more polymer only serves to weaken the gel. We can go ahead and try to investigate what's going on at the microstructural level and the dynamic level when we go through this reentrant rheological behavior. So the plot on the top shows the dynamics of the system. We're looking at a distribution of particle displacements over 2 seconds at different polymer concentrations. At low concentrations, we see there's a fairly wide distribution of of particle displacements, meaning they're free to move around, although we see a peak centered right around 0. This indicates that some of these particles are getting arrested, so they cannot move anymore, and you have a lot of these free particles that are capable of freely diffusing inside the sample. As we start to increase the polymer concentration, we see this more pronounced bimodal behavior. And beyond a certain point, adding additional polymer only serves to accentuate the arrested behaviors, meaning all of the particles, colloids that's available in the sample is now getting arrested and forming this gel. After we go through a critical concentration, though, through the peak in the rheology plot, we don't see any changes in the dynamic behavior, meaning all the particles are still arrested. We don't see them become mobile again. The snapshots on the bottom show 3D renderings of the sample structure of just the arrested particles alone. And we see that initially, as we increase the polymer concentration, we increase the number of particles that are getting arrested, but beyond a concentration of about 0.8 or so, we don't see any additional increase in the number of particles that are being arrested. So then how can we rationalize this behavior? So the operating hypothesis then in this case is that initially when we add polymer to the sample, all of the polymer has a chance to bridge one or more colloidal particles. So the addition of polymer in this case serves to stiffen the gel, serves to strengthen the gel that's being formed. Once we go through that some sort of a critical concentration, when you add more polymer, it might not necessarily bridge every single silica colloid that's available. So the bonds that are formed are weaker. So here's an example of really interesting rheology and trying to get insights by looking at the microstructure and dynamics. We don't necessarily see differences in the microstructure and dynamics, and by analyzing that, we can understand why the rheology or the yield stress starts to decrease at higher polymer concentrations. So all of the previous examples were with looking at the quiescent structure. Basically, you do your rheology experiment separately, and then you do your microscopy separately. Of course, in the real world, we're interested in looking at trying to connect rheology with or understand the structure as a sample is being deformed. And here is an example. Once again, we're looking at an oil-water emulsion, similar to what we saw previously, at a very specific concentration of the water. So this is an attractive oil-water emulsion, meaning you have a lot of droplets that are being formed, and at this 58% concentration, you essentially jam all these bubbles together. So you have some sort of a gel-like behavior. On the left, we're looking at the viscosity as a function of shear rate. Again, we see a shear thinning behavior as we start to increase an almost Newtonian plateau at low shear rates and then shear thinning behavior at higher shear rates. We also noticed that there's a pronounced normal stress that's being generated as we start shearing these samples. In this specific study, they used a Rheo optic cell to look at the structure of the sample under shear flow, and those micrographs are shown on the right. At lowest shear rate, we see a relatively uniform distribution of these droplets. The sample is fairly homogeneous. As we bump up the shear rate to about 5 inverse second, we can start to see the formation of localized domains. So there's a lot more large voids where you have continuous oil phase, and then the water droplets are starting to coalesce a little bit. As we increase the shear rate further, we notice the appearance of these elongated chain-like domains, rolling logs, which is what they are, concurrent with the appearance of the increase in the normal stress. So what's happening is there's an inherent elasticity in these materials that gives rise to the formation of these extended, elongated structures that gives rise to the normal stress, similar to rod climbing. And of course, when we go to much, much higher shear rates, the sample completely breaks down and you lose all structure of the discrete oil and sample phases. The next example we look at is a colloid polymer system, but in this case, we're looking at colloidal particles that are being forced to gel through the addition of a depletant. So these are steric stabilized PMMA colloids that are suspended in a density and refractive index matched solvent mixture. Matching the density means the particles are not going to sediment over time, and matching the refractive index means you have good quality for confocal microscopy. The gels used in the study are fairly high volume fraction, so about 40%, and the addition of polystyrene polymer introduces attraction between the colloidal particles via depletion. A custom-built parallel plate shear cell was used in the study that's capable of applying deformation at 70 Hertz frequency at different strains. And the microstructure and the dynamics were probed using dynamic light scattering, using light scattering echo technique, and 3D confocal scanning microscopy. The plot on the left to the top shows the autocorrelation function as a function of time at different strains. So what an autocorrelation function measures is basically how much the speckle pattern that you're seeing in scattering correlates with itself. So if the structure doesn't change, the intensity pattern that you have at 1 second will be very similar to the one that you have at 5 seconds and 10 seconds and so on. So that's what you see by that relatively flat line at low strains. As we start to increase the strain, we notice that the sample starts to decorrelate with itself, meaning the structure is undergoing some sort of a change. And then when you apply really large strains, it decorrelates really, really fast. And recall that we're doing this test at about 70 hertz frequency. So as you get to higher strains, you're essentially breaking the structure and bringing about some sort of rearrangement. The plot on the lower left shows a fit to an exponential fit to the autocorrelation function shown on the top. And they define a time scale associated with the decay of this autocorrelation function. And they notice that at low strains, we have really long sample relaxation times. And when we get above a certain strain value, the autocorrelation function starts to decay fairly fast. Now, of course, we want to try to look at the underlying sample structure, and that can be done with 3D confocal microscopy. So shown here are 4 micrographs of the structure using confocal microscopy. The first picture, labeled A, shows the quiescent sample structure, meaning before any strain was applied to it. It's fairly homogeneous. We see an even distribution of colloids and voids. The 3 other pictures, B, C, and D, show the structure after a strain of 15% at 70 hertz has been applied to the sample. We see the emergence of these locally organized domains, so we see local ordering within the sample structure. The inset in lower left for each picture shows the Fourier transform for this. So we, in C and D especially, we see the emergence of crystalline domains within the sample. And of course, if you're locally getting crystalline domains, that has to be offset by the appearance of voids elsewhere, and that's what we're seeing in sample in picture D. Of course, that was under oscillation. It's also relevant in terms of processing and handling to look at how the sample structure changes under flow. So this here shows results from a study that I was involved with. We're working with the same system, PMMA colloids suspended in refractive index and density match solutions, and polystyrene polymer to induce depletion interactions. But we're operating at much, much lower volume fractions, so 3.5%. So these are really dilute colloidal gels. I used a custom cone and plate shear cell to investigate how the structure changes. And this shear cell was designed to directly mount onto the stage of a fast scanning confocal microscope that allows us to track the changes in structure as the sample is being sheared. So one of the advantages of the cone and plate is you're not limited in terms of how far you can move in total strain. We'll start by looking at bulk rheology results. So the sample is being sheared at a fairly slow shear rate, 0.07 inverse seconds. And we're looking at the evolution of stress as a function of time over about 20 minutes. So we see that the stress initially increases for the first about 600 seconds or so, goes through a plateau, and then gradually starts to decrease from then on. So what is going on with the structure that gives rise to this? If we take 3D snapshots of the structure as it's being sheared, we notice the emergence of these elongated chain-like domains that are immobilized early on in the test. And these chains are oriented along the extensional direction of shear flow, meaning they're forming these stress-bearing domains inside the sample. And of course, that is going to result in an increased stress. At later time point, we see free flowing. We notice that the sample starts to flow and the appearance of these clusters. So that happens at later states. What happens in the intermediate region, marked regime 2 on the picture, is gradual rupture, where you have a competition between chain elongation and chain rupture that gives rise to the stress plateau. This is, of course, at a single shear rate. We've also investigated this as a function of different shear rates. At low shear rates, the top panel on the top shows a mosaic structure under quiescent conditions. You can see that the structure is fairly uniform before we start applying shear to it. And as we apply shear, we bring about these shear-induced changes in the sample that are dependent on the shear rate that it's being subject to. At low shear rates, we see the formation of these large colloid-rich domains and solvent phases and large voids. And then as the shear rate is increased, we start to rip apart these clusters and results in a more homogeneous distribution of much smaller clusters in the sample. Each of these mosaics is about 1 millimeter across, so they've been stitched together by taking multiple images within the sample. Of course, all of these previous studies that I've shown have required either the development of a custom shear cell where we can apply some sort of a deformation to the sample, or just resorted to doing independent rheology and microscopy. With the introduction of the new modular microscope accessory for the DHR, we have an integrated solution available now where it's possible to do bulk rheology and observe the sample using microscopy at the same time. What we've essentially done is to build a microscope that sits directly on the frame of the rheometer. The microscope accessory itself comes with a 3D stage that's micrometer controlled. It gives you access to a wide range of viewing positions. The sample is illuminated using an LED light source. A fast camera captures the images. Temperature control is brought about by the upper heated plate. And the accessory itself uses industry standard Nikon objectives to observe the sample. We have a couple of different options that are shown here, which is the optional optics plate for counter rotation and a vertical piezo stage that can be used for either 3D structure visualization or for velocity profiling, and I'll get to that in the following slides. So key features of the modular microscope accessory are that it directly mounts to the DHR frame, and it's a compact modular design. Mounting to the frame of the rheometer has a couple of advantages. You don't need to align the accessory with respect to the rheometer. And it also helps to minimize vibration because you're mounting the rigid frame of the instrument itself. We have a micrometer-controlled stage that gives you access to different viewing positions along X, Y, and Z, not just limited to a single window of observation. The system comes by default with a fast-speed camera that goes up to 90 frames per second. Not a high-speed camera, but fast enough to capture transient behavior. It includes Brightfield and Fluorescence microscopy, Brightfield and polarization microscopy with an optional fluorescence. And we have active temperature control using the upper heated plate up to 100 degrees Celsius. And all of this is fully integrated with the Trio software for capturing images, movies, time-lapse movies, 3D structured velocity profiling during the course of the experiment. The accessory is designed to accept standard microscopy objectives, as I mentioned before, for flexibility. We've tested this with 20x and 40x objectives with the 1.1 millimeter quartz plate. We also have the option to use oil immersion objectives, so this would be 50 or 100x objective, and we have the option to use thin cover slips as well. To give you a flavor for the general field of view, with a 20x objective, we're looking at a field of view that's about 320 microns by 240 square microns across. The accessory can be coupled with an optional stage for counter rotation to observe features that are stagnant zero velocity plane, and I'll show some examples of this later on. And we also have the option to use a piezo device for fine adjustment of the objective during the test. So this allows us to take 3D slices of the microstructure by systematically stepping the objective with 0.1 micron or 0.5 micron resolution or better, up to a distance of over 100 microns. Right? So now in this section, I'll talk about some qualitative results where we're observing samples under shear flow. Just to give you a flavor for the image quality that we can get with the microscope accessory. So all of the samples that are used in the rest of the talk are commercially available. The tests were done using a 40 millimeter parallel plate under controlled temperature conditions. And the sample was illuminated using a blue LED light source and observed using a 20x objective. Video capture was typically done at 30 frames per second, except in some cases where we needed to go at much higher frame rates. So here's an example of representative images from Brightfield microscopy. So the image on the top left shows a calibration grid. So again, we're looking at, with the 20x objective, a field of view that's about 320 microns by 240 microns. The image to the right, top right, shows 7-micron fluorescent spheres that are commercially available. And you can see the presence of some ordering in crystalline domains, local crystalline domains with this specific sample, fairly monodispersed. Bottom left shows glass spheres that are suspended in PDMS. You can see the image quality is sharp enough to clearly show the boundary of each of these individual spheres, as well as some defects inside the glass spheres as well. And on the bottom right, we have a 3D scan. So this is basically a video where we're stepping through the structure and collecting a snapshot of the 3D structure of the sample with hollow glass spheres. We're positioning the piezo at different, at 50 microns, 50.5 microns, 60 microns, and so on, systematically stepping through, taking a picture at each point, and getting an idea of the 3D structure of the specific sample. Here's another example of Brightfield microscopy. In this case, we're looking at an emulsion under shear flow. This is a PDMS and PIB blend that's tested at 80 degrees C. The sample was sheared at a fairly low shear rate for about 1 hour, and then subject to high shear rate, about 50 inverse second for just 1 second. And the sample was allowed to relax. So this here is we're showing just the high speed, high shear portion of the video. And you'll notice that we have some of these, we're able to observe droplet breakup, droplet elongation. And this is a video that was captured at 90 frames per second. Here's another example of an emulsion. This is just a water and oil emulsion. And in this case, we're shearing the sample at a steady rate of about 1 inverse second. And we record the video under both standard and counter rotation conditions. So under standard conditions, we see the emulsion droplets are going past the field of view fairly quickly. So if we wanted to track a feature across time, there's not a lot of time left for that. And we can get around this problem by using counter rotation. So what happens in counter rotation is that we move both the top and the bottom plates in opposite directions at the same time. So when you ask for a shear rate of 1 inverse second, we can specify a counter rotation ratio. So if we said 10 or 15%, the top plate would move at a velocity 90% of the commanded shear rate, so it would move at a rate of about 0.9 radians per second, let's say. And the lower plate would move in the opposite direction at a rate of 0.1 radians per second. The net velocity gradient across the sample continues to remain the same, but we now are able to hold features in the field of view for longer to observe this. And that's what we see when we play the video. So we can see the individual emulsion droplets are not just whizzing past the field of view, but we can actually track them across time. So this is really helpful. And by changing the relative ratio of the velocities, we can change the position of where the zero velocity plane or stagnation plane occurs within the sample. The next example we'll look at is with cross-polarization microscopy. In this case, we're looking at a light crude oil, a Pennsylvania crude oil, that was subject to a cooling temperature ramp. So with crude oil samples, as the sample is cooled, it undergoes a transition where some of the individual components of the crude oil start to precipitate out. They crystallize and they form a wax. And this is marked by a dramatic increase in the sample viscosity. This is, of course, a problem when you're trying to pump crude oil across several miles. And if this happens, and if it's not mitigated, you could run into the problem where the pipes start to clog up. So it is important to understand this behavior. The plot here shows an oscillation temperature ramp where we're cooling from about 25 C down to 0 C, and looking at the change in the complex viscosity. And we can analyze and find that the complex viscosity starts to diverge at about 15 degrees Celsius. The video here shows a time-lapse video under an identical temperature profile. So early on in the video, we don't see any elements that have polarization. So you see that the video is completely, field of view is completely blank. And then as the sample is cooled, we start to notice the emergence of these wax precipitates that are polarized, and then you can pick them up. The same experiment done with Brightfield visualization will be completely blank because you don't see the appearance of these individual components. So this is an example where cross-polarization can show you additional information that just Brightfield cannot. Right. Here's another example with cross-polarization microscopy. In this case, we're looking at starch gelatinization. So this is just 5% cornstarch in water. And we'll notice that as we're starting to heat up the sample, initially up to about 50 degrees Celsius, we don't see much of a change in the sample rheology, nor do we see any changes in the video. So we see the individual starch particles that have some sort of structure that gives rise to polarized signature. And then as the sample, right at the point where the sample starts to, sample storage and loss modulus start to go up, we start to see that the individual starch particles lose the polarization. They start from these crosslinks. So here's another example where we can use microscopy to link what we're seeing in terms of rheology, in this case starch gelatinization, with the disappearance of polarized elements in the sample. So all of the previous examples that we've looked at in the emulsions, crude oil, and the starch gelatinization, we've had some element in the sample that has allowed us to image it. This could be either the discrete nature of the emulsion droplets or the presence of elements in the sample that give rise to cross-polarization. But that is not necessarily the case always. So here's an example of a cheese sample. Cheese has both aqueous and lipid domains in it. It is an emulsion, but trying to visualize it under Brightfield microscopy, we wouldn't be able to see anything. One way we can improve contrast and generate good quality images is to use a dye that selectively stains one of the two phases. In this specific case, I use Nile red dye to stain the lipid phase. The same principle can also be used for other emulsions like mayonnaise, where we want to look at one specific phase. So in this case, the cheese sample was subject again to a temperature ramp. Start at about 10 degrees Celsius. All of the images in the slide have been given false color just to improve visual clarity. So we start at about 10 degrees Celsius, and as we ramp up the temperature, initially we don't see much of a change in the micrographs. When we get to about 40 degrees C, right at the point at which the tan delta starts to increase, we see some appearance of increase in the size of the fat domains. And then as the temperature continues to increase, we don't see much of a change. But then at about 80 degrees Celsius, right at the point at which the sample's storage and loss moduli start to cross over, we see that the lipid domains in the sample have gotten fairly large, and the aqueous phase, continuous phase, is really dark, meaning all of the lipid domains have started to coalesce together, which is why you're able to see the presence of these red globules inside the sample. In the last section of this talk, I'll talk about how we could do quantitative rheomicroscopy. So previously I showed examples of collecting pictures and videos during rheological tests that can be used to gain qualitative insights. So we notice that the lipid domain is increasing in size, or we're seeing the elongation and breakup of emulsion droplets. In this case, we'll go one step further and analyze the videos that we're collecting. So for all of these tests, I used commercially available polystyrene spheres that are fluorescently dyed, about 7 microns in size, and collected videos during rheological tests. The resulting videos were analyzed using publicly available image processing routines. These are available both in IDL, MATLAB, and Python. ImageJ can also be used for image processing if needed. Just briefly, in terms of image processing, what we do is we start off with the raw image. We apply a bandpass filter to remove some, filter out some noise. And then the image processing algorithm goes through the image and tries to find pixels of local intensity maximum. The working hypothesis here is if you have a spherical particle, the center of the particle is going to be the brightest pixel in the sample. We can then identify these spheres, and the image to the lower right shows a circle drawn at every center that we found. So visually, we can see that the algorithm has done a fairly good job at identifying all the particles that we can visually see. And we can tune the sensitivity of this image processing algorithm. So we can make it more sensitive to pick up particles that are just outside the frame of view if we need to, or just tune it down so we only selectively choose particles that are in the frame of view, so we have a consistent baseline that we use to analyze all the particles in the video. So in terms of image processing and quantitative analysis, the first thing that we look at is looking at the average particle velocity along the shear direction. Once we've identified particle locations, we can compare particle locations between two consecutive frames in the video. And we can locally search between time t0 and time t.1 seconds in the vicinity of where the particle is and try to find out where it moved. And if the particle didn't move too fast or too much, we can then link the particle and get the trajectory. Once we have a trajectory where we have particle location across time, we can then go ahead and get particle velocity across time as well. So, and that is what we're going to do here. So we're going to look at average particle velocity, and all this does is look at a particle's position at time t and where it is at time t minus delta t, and average that across all particles that we see in the frame of view. And we can do this along the shear direction. The test sample that I use for this is just a Newtonian fluid, just glycerol with fluorescent polystyrene spheres mixed in with it. And this was just a constant shear rate test under isothermal conditions at 3 different shear rates. At each shear rate, I recorded microscopy videos at different heights along the gradient direction, and I'll expand on that in the following slide. This was done using the piezoceramic device. And then the videos were then analyzed to look at the average particle velocity along the shear direction at each location. All of these videos were recorded at the radial location that corresponds to the average applied shear rate. This is the point at which we report the shear stress, and that is about 76% of the plate radius. So what we do is basically go at 5 microns, first focus on the lower cover slip using the piezo device, set it to 0 microns, and then step up to 10 microns, record a video, 15 microns, record a video, 20 microns, record a video, and so on. So we're taking snapshots, 2D snapshots of particle velocities at different heights from the lower glass plate. And then we analyze it and get the average particle velocity. And of course, we expect to observe a linear velocity profile, and that is exactly what we see. The dashed lines are straight line fits to the data points, and it's in excellent agreement with the global shear rate that is being applied, which is what we would expect. The next type of sample that we'll look at is a yield stress fluid. In this case, these fluorescent particles were added to a commercially available hair gel sample, and the sample was subject to a series of creep recovery tests. So we applied creep for about 2 minutes, and then allowed the sample to recover for 4 minutes before repeating it at a higher stress. All of the microscopy video recorded during the creep step, the 2 minutes, was processed and analyzed to look at particle dynamics. So here's a look at the bulk rheology of this material. So we're looking at the compliance and the strain as the sample stress is increased. So initially at low stresses, 5, 7, and 9 pascals, we see that the strain and the compliance are essentially flat and the sample doesn't move much. Then once we get above 13 pascals or so, we see an uptick in both the compliance and the shear strain, indicating that the sample yields at 13 pascals, and that is the yield stress for the specific material. We can then go ahead and collect videos. So here are the videos for the creep recovery, recorded just during the creep test at 9 and 13 pascals. You'll see that initial movement corresponding to the application of shear stress. With the 9 pascal video, we don't see much of a move. Again, this is below the yield stress of the material, so nothing happens across the 2 minutes of observation. These videos are sped up 4x, so with a 13 pascal sample, we'll gradually see it yield and flow, and at the point at which the sample starts to yield, we'll see a gradual translation of the tracer particles along the shear direction. Right. We can then go ahead and once again identify particle centers and track and quantify this type of behavior. In this specific case, I'm calculating the mean squared displacement of particles. What that tells you is the average displacement of particles over a tau-second interval. So basically, you look at a particle position at time 0, and then look at the same particle's location 1 second later, 5 seconds later, 10 seconds later, and so on. If the sample, and you average this across all the particles in the sample. In a liquid sample, there is nothing restricting the motion of particles, so you don't expect to see the particle at the same location. Particle displacement is always increasing as a function of time, so you would see the mean squared displacement linearly increase, systematically increase with time. With a solid or a gel sample, the tracer particle motion is essentially restricted because of the matrix, so the MST is more or less flat and independent of time. And that's exactly what we see here. So if you look at, on the right, we have an XY plot of the particle locations. So each time we found a particle, I put a dot. And we do this for all the particles that we saw in that 2-minute video we played earlier at both 9 and 13 pascals. At 9 pascal, we see that initial move, and then all of the particles are more or less immobilized. Whereas at 13 pascals, we see streaks indicating that these particles are being translated along the shear direction. And sure enough, when we quantify this behavior with the mean squared displacement, at low stresses, we see that initial displacement, but the particles are essentially arrested, so the mean squared displacement is more or less independent of time. Compare that with what we see at 13 and 15 pascals. The sample is yielded, now it's starting to flow, so the particle displacement systematically increases as a function of time. So we're able to quantify how much the particle moves after it's yielded. The final example that we look at is a sample that undergoes a phase transition. In this case, I'm looking at a commercially available gelatin dessert that's doped with the fluorescent particles. A sample was prepared and loaded on the rheometer at 65 degrees C, so it's in liquid state. And then it was gradually cooled at 1 C a minute from 65 to 4 degrees C, and then just allowed to equilibrate at 4 C for about 1 hour. During the temperature ramp, I recorded microscopy videos that are about 2 minutes long at discrete intervals. So we're spanning about 2 degrees Celsius in the temperature domain here. So we look at the rheology first. So initially the sample is liquid-like, so the sample's loss modulus is greater than the storage modulus. And then as we cool the sample down at about 20 degrees C, we see a crossover between the storage and loss modulus. And then from that point on, the storage modulus is much higher, indicating the sample is more or less gelled. And we can look at the individual videos. So if we look at the video at 25 degrees Celsius, we see that the sample moves a little bit, not much, but we still are able to see some local movement of the individual particles, whereas at 15 degrees C, they're more or less immobilized, confirming that the sample has gelled. We can quantify this behavior by looking at the self part of the Van Hoff correlation function. What this does is it basically describes the probability distribution of particle displacements across at a specific time. So you look at the particle location at initial time, and then 5 seconds later or 10 seconds later, and you find out on an average how much have these particles moved. So you might have a few particles that have moved 2 microns, you might have a few particles that have moved 5 microns. So you generate a histogram and then a probability distribution of particle displacements over a certain delay time. If we had a liquid-like sample, once again, the tracer particles are free to move in any direction. So you would see a Gaussian distribution of particle displacements, with most particles remaining right around their initial location. And if you had solid or gel samples, the tracer particle movement is restricted, so you'll have a very narrow distribution of particle displacements. And that is exactly what we see. So at high temperatures, 30 degrees Celsius, we see a pretty broad distribution of particle displacements over a 10-second interval. So particles can move up to about 4 or 5 microns. And then as we gradually reduce the temperature, this distribution starts becoming narrower and narrower. and then below about 17.5 degrees C, particle displacement is more or less restricted to about 1 micron. Now the noise at the lower temperatures is just a trade-off between your imaging size and the particle, or the image magnification and the particle size used. So the greater your magnification, the better you can resolve particle centers of the particle, and the noise becomes much narrower. But of course, if you use a high magnification objective, you see lesser number of particles in the field of view, so there is that trade-off. But again, this behavior quantifies this trend quantifies the behavior that we see in the videos, in that we have a gradual decrease in the distribution of particle displacement as the sample gels. With that, I'll quickly summarize, and I hope to have highlighted the importance of direct visualization as a valuable tool in trying to understand and link bulk rheology with the sample's microstructure and dynamics. The new modular microscope accessory for the DHR is an excellent tool where it provides a turnkey solution for observing samples under rheology during rheological tests, be it temperature ramps, flow sweeps, or creep tests. And gives access to a wide range of microscopy modes, including Brightfield, cross-polarization, fluorescence, and counter-rotation. And not just qualitative analysis, it is possible to observe these videos and quantify them using advanced image processing techniques to quantify the extent of deformation-induced microstructural and dynamic changes. Thank you for your attention, and I'll be happy to answer any questions.
Thank you, Bra. A recorded version of this webinar will be archived and available through the TA Instruments website.